Hello, everyone. This is Deborah Baker with Trusted CISO. And today we're doing this live stream with two cryptographers. This is for Crypto Done Right, which is a nonprofit. And you should go, check out the website, cryptodoneright.org. It's about giving you practical information around cryptography. So how to correctly, configure your web server around TLS, things like that. So we're going to be talking about post-quantum today with the rise of the quantum computers and how it's going to affect cryptography and the changes that need to be made. So first I want to introduce, we've got Scott Fleurer. He's a cryptographer with Cisco, and I used to work with Scott. Welcome. And I don't know if you wanted to say anything.
I'm just wondering if I'm the reason you left Cisco.
Oh, good one. And then we
That's
have
a rude
Mike,
question to ask on live stream, Scott.
Yeah. We've got Mike Ownsworth, he's with Interest. He's a cryptographer with Interest. I used to work with Interest, but it was way long, like late 90s, early 2000s. So I don't think Mike was there then. But I wanted to say that Mike has been named an award finalist in the Microsoft Security Excellence Award for 2023, which is super awesome. So I wanted to make mention of that.
Thank you.
Now, is there anything else that you want to say in your intro, Mike?
Yeah, I feel like Scott should have talked himself up a bit more. Maybe I'll do that in passing here. Yeah, my day job is security testing, application security testing, and I do cryptography sort of as a side hobby, but have gotten very involved in the post-quantum, the theory, the practice, especially the migration and transition aspects of it, which I think are going to be very challenging. And that work brings me to people like Scott and to organizations like Crypto Done Right. For all of Scott does a ton of groundbreaking research work and writes a ton of really useful technical specifications, and Crypto Done Right does a really great job of socializing this and giving concrete guidance. So I'm super happy to be involved with all of this.
Yeah, and I've been working in post-quantum crypto for, I don't know, 6, 7, 8 years. I don't remember exactly. And I really appreciate people like Mike, who comes in and adds to the practical details as opposed to the theoretical details I tend to focus on.
That's great. That's awesome. So, okay, so first question. So with the growing popularity and advancement of quantum computing, what do you think are the most significant challenges that cryptography will face in the future, and how can we overcome them?
Okay. First thing is we've got a lot of crypto all over the place, and we don't necessarily know where all that is. Crypto hiding in basically authentication for your refrigerator, for example. A lot of that is going to have to be updated, and we have to find that. In addition, one of the things that we have some nice primitives to do the simple post-quantum algorithms of signatures, key exchange, public key encryption, and that covers about 80% of the use cases. But there is this other 20% of which things which use more advanced crypto, such as direct IBE, identity-based encryption. Actually, I won't go through the list. And we need to have ways to deal with that, because some of the things we do with crypto really relies on those more advanced primitives.
Scott, I'm going to slow you down here. Put on my devil's advocate hat and make you think on your feet. Isn't there a chance that we as a society will never build a quantum computer big enough to run Shores that can break RSA 2048? Convince me I need to care.
Yeah. Well, yes, that is certainly a possibility. I can. However, that's not a security assumption that I am comfortable with making. I don't believe that many people are comfortable making.
Okay, so we'll admit here on this recording that it is possible. It's possible that we're jumping at shadows. It's possible we're doing a lot of work and doing a lot of disruption that won't actually end up being necessary. We admit that, right? Okay. But yeah, risk. I mean, you sort of mentioned risk or assumptions I'm not willing to make, and I think that's the point to start with. I'd like to quote the Global Risk Institute, that study that has been popularized by Professor Michele Mosca, that interviewed a bunch of experts, and they found, if you sort of squint at those graphs a bit, it's maybe there's a 1 on 8 chance that RSA will be broken by 2030, and maybe a 1 on 2 chance by 2040, something like that. And I guess to a non-cryptographer, 1 on 8 or 1 on 2, that's a pretty low risk, but to cryptographers, we much prefer risks that are, 2 to the minus 64, 2 to the minus 128. If I said there's a 1 in a million chance, that's only 20 bits of security. So, yeah, I'll answer my own devil's advocate. It's basically the same way Scott did, that even if there's a 1 on 8 chance, there's only a 1 on 8 chance that this is real, and it's probably more likely than that. But even if there's only a 1 on 8 chance, that's still enough to make cryptographers sweat. If I said there's a 1 on 8 chance that RSA was broken, we would get it out real fast. So yeah, the question 0 to Deborah's opening question is, do we even need to worry about this? And the answer is, regardless of whether quantum computers come to fruition at the size and speed we need for breaking cryptography, I still think all this hoopla is worth the effort.
Yeah. In addition, one of the things that this does as a side project, a side effect, even though it's probably not the main justification, is if a classical computer just happens to figure out how to break RSA, we've got alternatives.
And yeah, and for those of us who've been watching the cryptographic advances, the Fujisaki Okamoto transforms, the rolling in nonces into the signature primitives to make them non-deterministic, and these are all really good cryptographic advances that we can't really bootstrap backwards into RSA and elliptic curve, but we get the chance here to build new primitives properly, based on the current modern best practices for crypto design. So there's definitely advantages to moving to the new stuff, even if quantum computers don't turn out to be the reason, right?
Okay. Yeah. I mean, because, well, a lot of the encryption that we've been using has been around a long time. So, I mean, that's
which is actually not necessarily a bad thing. Our ideal thing is using crypto, which has been around for a long, long time, been hacked out by different people, lots of different people, and it's still not broken.
That's a good point.
That's it's all about trust, and that's what we will trust the most. We don't trust necessarily the stuff which is shiny brand new.
Now, one of the things I was going to say is that, I mean, I'm not an expert like you two, but I do know that symmetric keys are supposed to be secure, remain secure, but it's the asymmetric that can be broken, where you get the public key and then the quantum computer can figure out the private. Do you want to talk a little bit more about that?
Yeah. For symmetric keys, there is a generic algorithm called Grover's algorithm, which supposedly halves the key length effectively. It doesn't actually work that well, but even if it did, all we have to do is double this key length, use AES 256 rather than AES 128, and we're still perfectly secure. Easy solution. The problem with the asymmetric algorithms is that our current the algorithms we currently use are based on one of two different problems: factoring or computing discrete logs. If you can break those two problems, you can solve basically almost all of currently used public key algorithms and
traditional.
Yeah, traditional. And the problem is that quantum computers, we're using Shor's, could if it's big enough, fast enough, have enough qubits, can solve both. The whole effort behind post-quantum cryptography is to find public key algorithms for a quantum computer cannot solve, and also, of course, a classical computer can't either.
It's like with anything that deals with quantum physics, it's hard to have an intuition on these sorts of things. I've heard a really good metaphor, probably attributed to Michele Mosca, but the metaphor of seeing that quantum computers are good at looking at data in aggregate. Quantum computers specifically are built on wave functions. It's the physics of waves. And so they excel at the types of problems where you're trying to pick out periodic or repeating patterns out of a large data set, which complements our current computers very nicely. I mean, our current computers, if I give you a data set with several million rows and I ask you, to do some aggregate statistics on the data, well, the computer has to go row by row by row. Quantum computers are much better at looking at the data as a whole and picking out large sort of wavy type trends. Scott's nodding along, so I haven't said anything wrong so far. And the problem, and it just so happens that both RSA factorization-based cryptography, as well as the discrete log and elliptic curve discrete log problems, all sort of look a little bit wavy if you squint at them properly. They're repetitive, they're periodic, they're based on modular groups with a high amount of repetition and periodicity involved, and that's what gets us into trouble. So Scott mentioned Grover's and Shor's, which are both algorithms that have been published since the 90s. We've known about those algorithms for a long time. I've heard the question, how can you be confident that you're designing crypto? We haven't even built a quantum computer yet. How do you know that the crypto you're designing is going to be safe? How do you know there aren't more algorithms we haven't discovered yet? And I'm not a physicist. I'm not a quantum algorithmist. But I think we do have confidence that we understand in principle the types of problems that are difficult or easy for quantum computers. We understand that this periodic group structure is the source of the problem. And therefore we can define algorithms that do not have any of that structure anywhere to be found. And therefore we are as confident as we can be that there will not be an algorithm that runs on a quantum computer that will be able to break the non-periodic stuff. And now Scott gets to tell me whether I've said anything grossly wrong.
I would actually express it a bit slightly differently, but effectively it comes down to the same thing. We actually, while we don't have a non-toy quantum computer, we do have a good understanding of what sort of operations would be possible with a quantum computer. And so from that, we can use that to explore what sort of algorithms it can do, and which ones that they apparently cannot do.
Hello?
Yeah.
Yeah, sorry I'm late. I was in another meeting that ran long, but I got the tail end of what you had said about this sort of setting the stage for quantum resilient algorithms and how can we start testing them now? Because you need a longitudinal study to have confidence that they can't be broken by classical or conventional computers. And I think of the 4 that NIST had in round 4, right? Half of them were Kyber crystal and the other half were dilithium crystal. 2 of them have already been broken by conventional computers. One of them was a single core, commodity machine. So they're going back to the drawing board and they're saying, okay, guess what? We're starting over. We're asking everyone for fresh ideas on quantum resilient algorithms because, you're right. You need to have a testing period in order to be ready to swap them in, start testing them, and see if they can be broken. One of them was broken, though, with a side attack, right? Which is, you can break RSA with that today.
Side channel attack is an attack on the,
power consumption, right? You can tell the length and everything. Yeah. It's an attack on the implementation, not on the math.
Yeah.
But I wanted to introduce myself real quick. I was invited by Deborah to be a part of this discussion, and I wish I could have ended my other meeting right on time. But did I miss the introduction round? Do I have to say why
Yeah.
I'm here or what I think is fascinating about.
Oh,
the
you can
world
go.
of
Yeah,
computers?
go ahead and introduce yourself and everything. So,
Okay. So my name is Mike Wilkes. I'm a CISO at a healthcare startup. Previously the CISO for Security Scorecard, a security ratings company, scanning the internet every day. And before that, I was the CISO at ASCAP, the American Society of Composers, Authors, and Publishers. But most people like to hear stories I tell about my time at Marvel, where I was the head of security at Marvel. And I like to joke it was my job to keep Iron Man safe. So that tagline and joke out of the way. I'm also a member of the World Economic Forum in the Quantum Security Working Group and working group on oil and gas and cyber resilience. And so we've been working on what can we do now to prepare for the day when someone does build a 20 million qubit quantum computer that can break RSA in about 8 hours, according to Shor's algorithm, as you mentioned. And what we can do is we can get crypto agile, right? Crypto agility is the ability to swap in these algos without a lot of disruption. And if you look back, moving from SHA-1 to SHA-2 took about 5 to 10 years. PCI, needed to get off of SSL v2, v3, and start using protocols like TLS 1.2 and higher. That took at least 5 years to eventually roll out to all payment card industry participants. So we're looking at a similar time frame, given that what have we reached? D-Wave, I think, has come up with a 5,000 qubit quantum computer. But the biggest one, it's a slightly different model than what's happening with, I think, Google and IBM, where they have about 400, 500 qubits. So we're still orders of magnitude away from that moment. But what can we do now, like I said, to prepare for it? What is the crypto assets? What secrets do you have that need to stay secret for 30 years, right? If you're the government and the military, but as a person, what about your DNA? You probably want your DNA to remain private for more than 8 hours, right? Your bank account password, you can just rotate it every 7 hours, and then it doesn't matter because they got your old password, but you rotate it with a password manager at a higher frequency than they can break it in real time. But they can still learn stuff, right? And that's what these BGP hijacks are all about these days, I think. Store the encrypted data now for the future date when you can decrypt it and learn all the interesting secrets. So anyway, that's my high-level intro to this topic.
The day when I get an email like, please change your fingerprint.
Yeah, assertions of identity should not be immutable knowables like mother's maiden name, date of birth, and fingerprint, retina scan. The OPM.
Well, you can change your you can change your fingerprint 9 times.
In November.
You can degrade your fingerprint by like melting it off, right, and become a ghost. Anyway, lovely to meet you all. I understand that this is just sort of a free-form discussion, maybe, or there was a lovely presentation someone made last month for the working group talking about quantum machine learning. It's like peanut butter and chocolate. They totally need to go together because they're both dealing with approximations of truth, not ones and zeros. And can you imagine if you could know the position and spin of every atom in the universe, you can predict the future according to the laws of mechanics and some quantum theories, right?
No.
The equivalent,
well,
well,
it doesn't work that way.
The analogy, though, is that if you knew all the threat actors and you knew all their telemetry, you could potentially, in like 5 seconds, predict all of the attacks, right? Because quantum and machine learning, they both deal with sparse data and assertions of truth and confidence intervals. And so this German group had published a wonderful white paper on the current state and future prospects for quantum machine learning. So if I'll throw it into the chat real quick, if that'd be useful for you all to read, if you haven't seen it.
Okay, yeah, that'd be.
Anyway, I did make some approximations.
Can I,
Scott, go ahead and unpack my my illegal analogies around.
Well, yeah, one of the things that I think I want to bring up is counting qubits is not necessarily the best metric. For one thing, is what at least for what Shor's algorithm would need is would need reliable qubits because it's actually modeling basically an abstract mathematical object. And any sort of small errors would propagate over time and come up with after the millions of operations you do, come up with completely random noise. So you need some sort of error correction embedded, and just counting qubits doesn't actually count for that.
Yeah, what I would offer in my defense of that oversimplification was that correct. Quantum storage is very unreliable. Most people like a database. You put in some value. Tomorrow it should be there. It shouldn't be like Heisenberg's cat. Is it alive or dead, right? or Schrodinger's cat, sorry, in the Heisenberg uncertainty principle, right? And so you need tons of redundancy in order to even reach 99.9% reliable quantum circuits. So a simple NAND gateway implemented in qubits, yeah, you're right. It's a rough measure, and it's not very cool because of all the redundancy. It's not a linear kind of thing. But if we're at 500 qubits now and we need to get to 20 million, you might have a reasonably reliable CRQC, right? A cryptographically relevant quantum computer per the NSA definition, which is the thing everyone's worried about, because there's no such thing as quantum.
Which I've heard pronounced crock.
A crock of flowers, yeah, or a crock of stew, right? But the fun thing I think about projecting, there could be some type of magical leap that someone makes in the technology, but there's no such thing as quantum incident response. It's not like a DDoS attack where you have observable behaviors of a botnet bringing 2 point whatever terabits per second of requests, amplified by, Peloton, bicycles and any other thing that happens to have an IP address on it that's a part of this attack.
Yeah. It's true. If the NSA builds a quantum computer, they're not going to advertise it. On the other hand, there are other interesting things that you could do with a real quantum computer, which would be more published. For example, modeling chemical reactions. That's very interesting. It's potentially worth lots of money, and there's no reason for anyone to keep it secret.
Correct.
Yeah,
and it's interesting because that's the non-pathological use of a quantum computer, is to model every single atom and come up with really cool batteries, good fertilizers, good ways of desalinization of salt water. But where's the chat where I can give you the link? I guess it's here. This is the German white paper.
Yeah.
That's our private chat. You want in comments, I believe.
Okay. Yeah. Let's see.
I'm gonna take Mike's comments. I'm gonna take Mike's point and go on a little rant of my own. We focus on the doom and gloom of quantum computers, but if we sort of think back to 2000, 2005, we had the internet, we had instant messaging, we had a whole new era of instant communications never seen before. We were starting to have databases full of useful data. You're starting to have every purchase made by a person on their credit card, and that data is starting to be centralized and accessible. But we didn't yet have the capacity to process that data at scale, what we think of as big data or ML. And if you think about, sort of taking a big step back, a lot of the societal and technological improvements we've seen in the last 20 years, a lot of that is from our ability to analyze data sets at that size. You think of, the logistics, getting stuff from an online retailer to my door in less than 8 hours. Like, all of that is driven by these big data processing enhancements. And that wasn't free. That required a whole generation of skilled laborers, the AI programmers, AI architects, statisticians, modelers. I imagine the quantum revolution will have a similar sort of feel to it, in that the size of data that we can analyze is about to grow, but the skill set required to write these quantum algorithms tailored to a specific data problem probably will have a similar feel, and we'll probably need a similar set of quantum algorithm experts working for all these big data companies and big data problems. I don't know how that relates to crypto, but it was definitely a thought that I think doesn't get discussed sort of enough.
It would certainly, going back to what was discussed, it would act as a canary about the problem becoming potentially being more real.
The other thing you can do is you could have a virtual encrypted tripwire where you could send a message with content and put it somewhere and put a URL in it or something, right? Host that URL, and eventually someone's going to browse to that URL, right? With that as like the referring document or the origin. And so you kind of like leave it, and once someone breaks your encryption and then browses that URL, they've tripped the wire, and you now know that your secure encryption communication has been intercepted. I think we might end up going back to just passing around more thumb drives, because then you don't have. Because if you think about it, in the future, there would be someone's going to order up a quantum tap. It's going to be a major plate tectonic shift, right? Destabilization of multinational, nation-state corporate interests, and you're not going to have it available because it requires, at least at the moment, a lot of resources, a lot of special rare earth metals, and you usually have to bury the computer well underground so it can't be detected with heat signatures from satellites. But basically, someone's going to order up a quantum tap and say, I would like to listen on this encrypted conversation at this point in time. So think of quantum attacks as a service. And you could potentially use deception and obfuscation in order to detect that someone's tapping your connection. And of course, the idea of like a quantum voting machine is fascinating, because if someone looks at your vote, they change, the observed.
So all you need to do is look at all the votes cast by people who are likely to vote for your opponent.
And you would change the thing that's observed. I think the quantum entanglement, right? This is like spooky action at a distance. And when people think about it, I like to harken back to Newton. Newton was a complete weirdo at the time, saying, yeah, there's this action at a distance. It's called gravity. And people are like, no, there has to be this thing called phlogiston, which holds the Earth and Moon in place. There has to be a medium by which our mechanical understanding of the universe allows these objects to stay, in an orbit. And of course, now Einstein looks at what's going on with quantum and quantum entanglement, or at least the idea of it, and he was calling it spooky action at a distance, right? Where you affect two different carbon atoms, that are hundreds of miles apart, by touching or influencing one, and they used to be a part of the same brick of, of a pencil or of a graphite or something, right? Is it true, if you go back to the ancient philosophers, like, is 1 ounce of gold unique or different, or is it an individual from every other ounce of gold or every atom of gold? And so if you think about it from a spiritual point of view, it's much more like Friedrich Capra's The Tao of Physics, right? Everything is just a constant dance of creation and destruction. And our Newtonian worldview and model of the universe has been completely, subsided by what we know about quantum physics. And I'm a bit of a dilettante in this area. I like to toss out names and books and references and analogies. But it is interesting to think about how there's so much space, right, between stuff and between atoms. If you look at the Power of Tens movie that the Eames family made, when you zoom in, there's like these great big periods of nothingness, and then eventually you reach like the protons, neutrons, and then eventually when you zoom out and you reach that galaxies, right, and you go in orders of powers of 10 every second, you notice that there's just not a lot of stuff to the universe. And there's enough space in all of that stuff, right, for my hand to pass through this desk. But there's not, because of all these probabilities of electron shells and valences and forces that cause my hand not to pass through the desk. But anyway, that's me getting a little bit mystical and Eastern on this discussion, which is more probably Western scientific rational. But I like to run the whole spectrum when I talk. So, have you read Tao of Physics? Are you familiar with Friedrich Capra's book?
Not.
He has a brother who made a movie, which is a really good movie. If you want the too long did not read version of his book, his brother made a movie called I think it was called The Turning Point. But anyway, it stars like Sam Waterston. It's a philosopher, a poet, and a politician, and they're out having a conversation, and they talk about all the stuff that's in Friedrich Capra's book, but in a much more accessible manner.
I like to pick one thing out of your monologue there. I think you mentioned breaking a quantum computer breaking an RSA key in 8 hours, somewhere in there. And I think there's some interesting points to be thought about there. We talk about quantum computers as in the advent of a cryptographically relevant quantum computer, as in on that day all encryption, falls open.
Correct.
And that's probably not right.
It's pretty resource intensive. Yeah.
Yeah, there's gonna. I mean, even once these crocs, if we will, exist, there's gonna be a limited number of them on the planet. Mm-hmm. Dozens, maybe small number of dozens of them at best, and hours per key they need to break. Probably never will my personal credit card be worth breaking the key for, right? There's no, the economic incentive to break my credit card and spend $2,000 is probably not ever worth it. And
Yeah,
I
just
don't
like
know,
ordering up a Pegasus, 0 day, 0 touch, where they took over Khashoggi's wife's, phone, and used the Pegasus group, to do that. You're not a high value enough target to expend this kind of resources on to
Well,
break,
that, and also, if you really, really wanted Mike's Ownsworth credit card, there are a lot easier ways to get at it.
Yeah, the XKCD comic showed up immediately, right? Where you take a $5 wrench and you beat me on the head until you give you my password, right? The comic I'm referring to, right? Where they're talking about, oh my God, it's encrypted with
certainly do.
4,000
Rubber hose cryptanalysis.
Exactly. Yeah.
So it's
not
sort of,
lost
you
on us
mentioned
in the
your
World Economic Forum. Yeah.
You mentioned your encrypted tripwire and see if anyone ever decrypts it and follows the link. I mean, you'd have to put that tripwire in something that there's a strong enough economic incentive to be worth spending however many dollars of
Correct.
quantum computer time it takes to break.
Yeah, you'd have to do something like nuclear.dod.mil and send a message to all of the bases around the world, and then embed it
with a link that says the secrets are here.
Yeah, stego it into a graphic as well, because people will detect the stego.
There are already tripwires. There's a lot of bitcoins out there who everyone has completely forgotten what is the public key, the private key for. What if someone starts going up and spending those?
Sure,
that's true. The coins belonging to Satoshi's account sort of are that tripwire, aren't they?
That's a very valuable asset. It is stranded at the moment, and I think one of the guys from Loftcrack actually recovered from a hardware key through a proper attack. Right, he was able to break the encryption, get the cipher, and get someone's crypto wallet recovered that had lost. They were one passcode, one attempt away from it wiping itself, and he was able to save them. He recorded a video about how to do it. But you're right, that would be a perfect honeypot transaction / asset to monitor.
Yeah, and it's all public.
Yeah, it'll be very
there's a question
when it happens. The blogs will light up once those coins get spent.
Yeah, Seth Nielsen asked, is it possible that a quantum algorithm will introduce new cryptographic encryption algorithms, aka not just break encryption, but give us that next generation level of cryptographic privacy and security? I think so, because remember, it's good at modeling things, and in my mind, what it's doing when we talk about quantum supremacy, we're talking about the ability for a quantum computer, which are all hybrid computers, by the way, right? No one's going to start typing at a 0 Kelvin keyboard attached to a quantum computer. So every quantum computer is interfaced with a classical computer, and there's always going to be attacks against the classical buffer that gets you to the quantum. But anyway, so if you are going to be doing this algorithm, you need to do something that surpasses the current most powerful classical computers, right? When the US and Japan are always fighting for however many teraflops, petaflops, exaflops, whatever they are, flops. And there's a Wikipedia page that tracks this, right? But you need to be able to surpass the calculation of classical before you reach quantum supremacy, right?
They're not faster.
No,
that's a bit of a fallacy. Just thinking about quantum computers are faster, because that's not.
They're better at solving a certain subset of problems.
True. Okay, difficult maths, which is what we call cryptography. Yeah.
Well, not even math. Like, you look at the QKD, the quantum key distribution stuff. A lot of that's based on photonics of quantum optics. That I'm gonna fire an entangled stream of photons down this fiber optic cable, and I'm gonna be able to detect if the stream gets broken at some point. There's nothing to do with math in there.
Sure.
That, and also
physics-based tamper detection.
A study of quantum cryptography beyond QKD. From what I understand, everything I've seen in that assumes very long-term storage of quantum state, and so it's not very practical. Maybe it will be at some point.
Yeah, the practicality.
The
I think
that's the challenge, right? That I did a hackathon. It was called Hacking at Random in 2009. You've heard about these camping trips in Europe where a bunch of hackers get together and they have a conference. Well, I got to do one when I lived in Amsterdam. And so there was a talk on quantum storage back in 2009 at this, and we built our own, cell network, and we had all these lovely, things launching, burning things and, catapults and rifles of squeezy sheep and things like that. Your typical geek camping in the woods hacker gathering. And that's where I got this first idea deep in my head that quantum storage is very unreliable, right? Because of the half-life of these types of things, and the fact that qubits are not at all like ones and zeros, right? So that's why you need all that redundancy. But I did want to add one last thought, because you're right. It's not just heavy mass, but if you think about cryptographically relevant quantum computer can break asymmetric algos, but it can't do anything against symmetric encryption. And the only problem is that we use asymmetric so much because I can't have Macy's issue me a certificate with the pre-shared key in order to browse their website securely. But if we could, and some of the paths forward are for people that own both endpoints, the laptop, the phone, and the server, they can just switch from asymmetric to symmetric, and then quantum is up Schitt's Creek, right?
So I think you've just answered your own question. The quantum encryption, as in encryption that runs on quantum hardware. Yeah, if we assume that there'll be at best sort of 12 of these machines in the world, having those 12 machines be able to talk to each other securely just doesn't seem particularly commodity or widespread. And yeah, at that point, why don't you just sneakernet a key on a USB stick across and use a pre-shared key AES mode?
Mm-hmm.
So I think there's probably super interesting academic and scientific work to be done with, what could we do if we had crypto algorithms running on quantum computers, but I can't see it ever being more practical or commodity enough.
Yeah, well, the quantum cryptography things that I've seen are things are based on mostly unclonability and trying to exploit that. And that is something that's a fundamental operation that you cannot do with classical, because of course you can copy classical bits anytime you want.
Sure. Yeah, and so if you have something that's tamper resistant in its fundamental nature, right?
Yeah,
but maybe we just want to go live
physical sense.
Yeah, maybe we just want to go live in a Star Trek utopia where there are no need for secrets. I mean, generation, TikTok doesn't really care about oversharing, right? So maybe this whole concept that we're hung up on privacy and secrets is just an old, meme that'll die out. I think of it as a pendulum. If you go back to medieval times, there was no such thing as privacy. Everything was in everyone else's business. It's only when we
I think people will always care about I can spend my bank account and you can't. There's going to be some problems that remain.
Not if we have a universal income. Not if we have matter compilers and you say,
even if you have universal income, I can spend my universal income and not you can't.
Right.
Go away.
I do try to come up with science fiction near-term stuff, like Neil Stephenson, if you've read his Diamond Age. He talks about a not-too-distant future where we have nanotechnology, matter compilers. Think of that as just the evolution of a 3D printer. Instead of extruding plastic in layers, we're informing nanites to go and assemble a Patek Philippe watch, right, atom by atom. And that way, that's the only thing I think that'll disrupt Amazon at this point. Logistics. Why can't I just walk to the local FedEx? They have a matter compiler. All they need is enough of the raw elements. They could print me a blanket. They could matter compile me, toilet paper. They could make me a Lenovo laptop, right? That's sort of, I think, where that goes down the line. This is all cocktail party conversation kind of level. What if?
Yeah, I do sort of agree that the path to the Star Trek replicator is atom level 3D printers.
Yeah, but it's actually possible. It makes a quantum computer looks trivial.
Correct. Yeah. Now, if you've never read the book, I highly recommend it. Diamond Age.
Yeah, I have it somewhere.
He wrote Cryptonomicon. He wrote Snow Crash, and he talks about a near future where there's these nanite wars going on, where you have swarm intelligence and swarm technology, and the air is just full of dead nanites. Right, the Chinese versus the Russians, or the Israelis versus the Germans, or something, or the Iranians, I guess, would be their nemesis. And so he calls it a toner day, right? Almost like what we experienced, with the forest fires here in New York. Instead of it being bits of burned trees, it would be the detritus of nanite level warfare. Anyway, really great writer. If the audience and listeners have never heard of Neil Stephenson, I recommend reading Snow Crash, the first book, then reading The Diamond Age, and then Cryptonomicon.
In the slightly closer future, I'm looking forward to not needing a cupboard full of dishes anymore. I'm looking forward to I just say, computer, please print me 4 place settings. Computer, please make me a cup of coffee. It makes the cup and that fills it with coffee. When I'm done, I just toss all the stuff in the dishwasher that melts it back down into plastic and feeds it back into the printer. I think that's probably slightly sooner than being able to replicate a Lenovo laptop. But I don't even know how close we are to being able to do that.
Actually, probably replicating a Lenovo laptop would probably be easier than actually replicating the actual coffee.
Yeah, the actual coffee part can stay with steam and grounds.
It depends if you're going
the cup to materialize.
It depends if you're going for Kopi Luwak or you're going for Starbucks, right? Kopi Luwak is a much more complicated, enzyme and molecular structure, which involves poop, in the digestive tract of a civet, a cat-like object, right? If you've seen The Bucket List, right, when Morgan Freeman and Jack Nicholson are talking about drinking the most expensive cup of coffee on the planet.
Okay, so
you could model it. You could model it with a quantum computer.
I want to get us back on track. Yeah. So, what do companies need to do now to prepare for these quantum computers?
Well, I have my pat answers. I'll get them out of the way quickly. You have to learn how to swap your algos, because eventually there will be a blessed algo, which will eventually make its way into a standard. The standard will eventually be implemented in a protocol, and the protocol will eventually show up in a product, right? And so you have to be able to move quickly, agility, right? But that's almost with anything. We could use that now, right? I mean, to get to TLS 1.3 or to do symmetric encryption for certain types of workloads. The other thing is, of course, categorize your data. Data classification is not static, right? Something that's secret today might be public tomorrow. So you need to understand which of your long-term secrets. So I have this idea of a TTL, right? The time to live. What is your data classification TTL? Because again, classification of something confidential secret or confidential restricted is not a forever thing for most data. When I worked at Marvel, for example, whoever was being cast as Captain Marvel was uber secret until the moment it's not, and then it becomes public. So you need to have a good data classification, data inventory, and know which things need to be protected by strong ciphers and algos that are quantum resilient, and which ones don't.
Yeah, for another example would be a company's annual report. It is extremely secret until it is released, in which case, and after that, it's public. So they don't care if it's. On the other hand, there may be company Cisco private information that they want to keep around 20, 30 years. Health data is another example. Other things that you just want to keep around for a very long time.
People bring up a lot the EIDAS sort of set of standards, the digital signing legally binding contracts standards that have weight in Europe. And that's an interesting case, because those are documents that are public. And so if we imagine you're signing, a contract that dictates the ownership of a large corporation or the deed of a large piece of property, someone could come back 80 years later and challenge the authenticity of that contract and say, no,
true, that's the integrity.
This was fake.
Of the CIA triad. That's the integrity part. When I give a course lecture on the CIA triad, I often talk about Wikipedia page edit wars, right? The integrity of the truth and the assertions of truth that live on like the Barack Obama page or the Donald Trump page, right? Okay, maybe that's not, a truth, right? It's always going to be perception and perspective, and people are going to kind of manipulate it and disinformation. But you're right, the provenance and integrity of a fact or a contract, and could it have been reverse engineered due to an unknown 0 day where someone could change the entity and it looks cryptographically valid, right? That could be an interesting attack in the future, sure.
Or alternatively, say challenging the authenticity because the private key has been exposed.
Yeah, well, that's why we have CRLF, right? Or certificate revocation lists, CRLs. You'd have to have some type of
timestamping
servers also play a pretty integral role.
Break someone's private, I'm saying is you break someone's private key and then saying, hey, that thing they signed over there can be signed by anybody. You can't trust it, even if they did sign it.
It feels like a similar problem to
these the other important part of these ecosystems is the timestamping authorities. So both like Windows code signing variance, and the whole EIDAS thing relies on timestamping servers. So the timestamping servers will provide their own cryptographic proof that this document existed with this hash at this time. And EIDAS in particular has modes to reiterate over all of your signed contracts every X years and reassert that these documents are still valid at this time.
It reminds me of one of the
EIDAS isn't totally hosted, but
one of the proof of life questions I had when I was teaching a webinar. The students were like, "Are you pre-recording this and just hitting play, or are you really delivering, the lecture live?" And so I had to come up with a way to prove that I was delivering the lecture live on a Saturday afternoon. And so what I did was I did a screenshot. Well, no, first I did a trivial example. I said, "Hey Alexa, what time is it? Right? What day is it?" And they're like, "Oh, you could just forge, the audio file of Alexa answering the question, right?" And of course, she's answering the question now.
She went off in the background.
I should always mute her before I go on calls. But and the funny thing, of course, was that's trivial to disprove, right? So I went on from there. I said, so I did a screenshot of the lecture slide with the participants, right, with the timestamp, and then I did a GitHub commit to the course repo for the students, which has a timestamp and a hash. And so that was the best example I could come up with, proof of live instead of proof of life. And so to me, it feels like you're talking about a little similar kind of problem. How do you validate your assertions of truth, right? Because eventually there's going to be some chain of trust.
I like the this morning's CNN headline was.
Yeah, that's typical hold up the newspaper showing that the hostage is still alive. We send the ransomware money, right?
Exactly. Yeah.
So Seth has another question. It says, for signatures, what about re-signing with new quantum safe signatures?
Yeah, and I'm not as familiar with EIDAS as I should be. I believe EIDAS does have a way to do that. So there are sort of some standards that can do it. That relies on being able to get your data and bring it back and re-sign it, which is often, I think, the hard part. And so, Mike, you talked about cryptographic agility. We could talk about cryptographic inventory, know where your crypto algorithms are. And we could talk about data inventory, know where your data is that's going to have aging crypto and know how to sort of bring it back and iterate over it. And not all cases are you going to be able to go find that data. In some cases you can. It's centralized and it's in a database, but often it's not.
Data is like water. It flows downhill. It wants to be shared. It's going to leave the barn. Have you heard of TDF, trusted data format? The NSA invented this. I put the Wikipedia link into the private chat if you can reshare it. This is a technology that's being used by companies like Virtru right now for client-side encryption for Azure and Gmail, which makes it easy for people to not be subpoenaed by Gmail, or a silent subpoena and give up your emails because you own the crypto keys. But TDF is kind of cool because you're encapsulating the policy in the data object itself when it goes out. So you assume the cow is going to leave the barn, but you write a policy that says this person can't read it after a certain date. So it's useful for contract negotiations. You can pull back the rights. It's almost like DRM on steroids, right? Because you can actually have this, like I said, encapsulated policy. One of the coolest examples I remember hearing about, I haven't seen it yet, but let's say you have a Word document, and the Word document has an appendix full of a whole bunch of incident response like details, right, from a root cause analysis of a breach. And you don't want the whole world to be able to read it. You can actually write a policy that'll redact dynamically the appendix and make it unreadable to a user based on their domain name or their fully qualified email address or some type of signature and key identifier. And so I think this is quite cool in terms of emerging technology. If more and more people played with TDF, we wouldn't have to worry about keeping the data on our own spindles, in our proprietary on-prem data centers. We could let it get out and be where it wants to be, like water flowing downhill.
Yes, but is it essentially based on attribute-based encryption?
I'm not sure. I'd have to read up on it some more, but I know that it was invented by the NSA, and the commercialization and open sourcing of it is fascinating. So,
yeah, the reason I'm asking
I'm looking at the
is
Wikipedia page
that
for the first time.
you probably you weren't logged in quite then, but one of the things I discussed is our lack of post-quantum advanced algorithms and attribute-based encryption is one of them.
Yeah, there's a bunch of fancy crypto stuff that we have yet to post-quantumify. Looking at the Wikipedia page here for TDF, my first question is whether it relies on either the clients being honest, like your document reader saying, "Oh, you shouldn't see this," and then just refusing to open it, or if it relies on the server being honest and refusing to serve it, or whether this is fundamentally cryptographic sort of time capsuling.
Mm-hmm.
Yeah,
I
useful
see someone
question
like the
for
NSA saying we trust our servers, but that might not be true, for general cryptographic problems.
It can't be like Azure Rights Management, though, where you have to phone home with a live.com account and then it determines what your permissions are, right? So the permissions and policy have to follow the data, and it can't rely on a server. So it has to be implemented in the format, as I recall.
So then why can't I just write my own client that ignores your rules?
I don't know. I mean, I imagine there's some type of assertion of identity involved. So you'd have to do some good spoofing to pretend to be someone else, and then the policy's not broken. You're just changing.
You might be pretending to be yourself only 1 year ago.
Yeah, just
no,
I've
that's interesting.
I've seen schemes like this before.
Yeah, I'm sure they've thought about it and has a good answer to that. I can't imagine what that answer is though.
Yeah. I'm just mentioning
trusted client or trusted servers, the two solutions I've seen to that problem.
Yeah, I just share the clever stuff I come across. I think these monkeys are pretty clever. Obviously, Google has gotten into the game now. They're doing client-side encryption, right? CSE, and they're making it a new thing because they don't want to have the rights to read your mail, right? Google wants to get out of the business of silent subpoenas and saying, okay, show me the communications between these subpoenaed users. And that's one of the reasons why the hedge fund I used to work at didn't want to move to the cloud, because they had high wealth net individuals which weren't necessarily legal, and they didn't want to have to respond to a silent subpoena where you don't have to tell the person that you're breaking administrative rights and access on the assets and reading their mail or reading their database or looking at the contents of their bank account, right? I think it's the same kind of thought about what crypto is up to, right? How do we have secrets? Why do we have secrets? What is privacy? What's the difference between privacy and secrecy? I think privacy is about your own data.
I'll build on that to bring us a little bit back on topic to post-quantum here. Scott mentioned the bucket of sort of fancy cryptography. We think about traditionally, hash functions, block ciphers, and asymmetric. But of course, there's this whole category of sort of privacy enhancing technologies, which includes blinded signatures and homomorphic encryption, like sort of that whole bucket of things. And one of the interesting ones in that bucket is the zero knowledge proofs, which factor into this conversation really well, because if the server wants to be able to claim that it cannot read your data, one of the hard problems there is how do I verify your password if I'm not allowed to know what your password is, if I'm not allowed to ever see it or handle it? And gets you quickly into the zero knowledge proof sort of area of crypto, which is a fascinating emerging field, but one that isn't going to move to post-quantum very gracefully. That we're going to need to reinvent a lot of fundamental primitives there.
Mm-hmm.
Interesting. Yeah, I had a good analogy of that. I was looking at a passwordless solution once, and there was this startup at RSA that was doing this because they had a zero knowledge solution. And their analogy to explain to people that don't understand what a zero knowledge proof is imagine there's a cave, complex maze inside of it, 2 exits, and you yell into it, come out the right side. And then the person who has knowledge of the cave comes out the right side, come out the left side, right? And eventually they do it right 100% of the time. You're like, okay, they have knowledge of the inner workings of the cave. I don't need to have knowledge of the inner workings of the cave. And so that was the analogy about because you can technically build a zero knowledge database where the custodian of the database does not know what's in it, but they can still perform operations on it and they don't have to respond to the silent subpoena because they technically don't know what's in the database. So yeah, I think that's a fascinating area. I have no idea what
they know that the clients know what's in the database, but they themselves don't know what's in the database.
Yeah. And Seth just asked if there's no post-quantum zero knowledge proof. I believe there is, but
there are.
I don't know the details.
Yeah, zero knowledge proof is one of those we sort of talk about it as if it's a single thing, but it's not just your favorite zero knowledge proof algorithm. The zero knowledge proofs, my understanding, end up being very highly custom tailored to the problem that you're solving. So there are zero knowledge techniques like snarks come to mind as a family of zero knowledge, but I do think you still need pretty high domain knowledge to actually take that framework and apply it to your problem. So there are families of zero knowledge proofs that I think are post-quantum, but I don't know if they apply to all problem families or not.
I do have one quick post, again, just maybe my last little bit of sidebar. It's not totally sidebar. Brian Lenahan has a really cool quantum newsletter, if you haven't seen it. I love reading it. It's on his Substack. And there's also a link I put in the chat from the University of Wisconsin, or I'm an alma mater, talking about 2 grants to push optical atomic clocks past the standard quantum limit, which is time and timekeeping is a fascinating element of all this, because we have these ideas of a leap second, right, where we move forward. But the Earth is slowing down. We actually need to do a reverse leap second in the future. And I was working at the CME when a leap second happened during business hours. And so people were wondering what would happen when there was a 60th second on a particular minute, when you're time stamping, right, with precision time protocol to the nanosecond, transactions, right, and trades on the exchange. And we didn't want people to game the system during that 1 second, right, and do like a what do they call it? Sub-millisecond crashes of the market and stuff. Anyway, so we did all this testing. We rolled our clocks forward, but I have no idea what's going to happen when we have a minute that has 58 seconds in it instead of 59. Right?
I love that example. Like, just talking of cocktail party conversation topics, speaking to friends who are not scientists or technologists, and what's the hardest problem in computer science? And I say dates. How many milliseconds are between now and the same date and time 100 years from now? You'd think that should be an easy problem to solve. Turns out dates are still surprisingly troublesome for programmers, for exactly the reasons you mentioned, for time zones, for leap seconds, it's dates.
Yeah, so Brian had written an article talking about quantum timing, and every week or every month or whenever he does it, he writes a new theme, and he's really good at this. I think he's a Canadian, if I remember correctly. And the Canadian have a whole quantum, strategy and national quantum strategy, and they're investing like a whopping 500,000 Canadian dollars in it, right? Which is nothing compared to what it takes to build some of these computers. So they're not really putting their money where their mouth is, or as they said. But it's certainly fascinating. There's certainly people doing.
I believe the quantum consortia grants through NSERC. I think there's hundreds of millions of dollars available through that grant.
Oh yeah, Europeans are really spending.
The Europeans are too, but I mean Canada in particular.
Okay.
They just announced the winners of the quantum consortia grants a couple months ago, and those are like individual grants for $5 million. So there is definitely money. I'm going to counter that one. There's more than pennies available from the Canadian government for quantum research.
Yeah, Mike's up in Canada, so that's why that's where he's at.
I received one of those grants, so
okay.
I'm aware that they're available.
Are you in Calgary? Because that I thought was like the quantum. Used to be bullets and manufacturing, and now it's moving to quantum campus.
I thought that I thought the capital of quantum it was Waterloo.
Yeah, so I'm on a grant with University of Waterloo and University of Calgary. Waterloo being the post-quantum and quantum computer research center, and Calgary is doing a lot of quantum networking. Yeah, and this is a combined grant effort between those two universities.
Well, thank you for letting me crash the party and go off topic all the time. It's my nature, unfortunately. But hopefully it was inspirational in some regards for being not entirely on topic. But.
Yeah, well, thanks everybody for joining. I thought this, went really well, and thanks again. And then I'll see everybody on our regular Crypto Done Right call too. So thanks again.
Okay.
Thank you for organizing and
Bye.
hosting, Deborah.
All right.
Thank
Yeah,
you.
nice to meet you, Scott. Nice to meet you, Mike. Thanks, Deborah, for the
Likewise.
invite. Hopefully you'll let me
Okay.
come back sometime. I'll try to be a little more
Yeah.
focused next time, maybe.
Okay. All right. Bye.
Okay. Cheers.